Hi everyone, so this is the last lesson of the power generation and transmission topic. We've had 4 lessons so far and this is number 5. So if you weren't here, well, if you weren't at school for the last 2 lessons, then you're going to have some time to catch up over the next 2 days. There'll be some stuff about, say, generators and Lenz's law, which you'll get time to go through, and for the others you'll get time to revise, because the plan is that if we're back at school next week, we'll be doing the SAC, both SACs across the 3 lessons that we've got. So just to give you an idea, there'll be one SAC that you do on the Tuesday, Wednesday that's going to go over those 2 lessons. It'll involve, you have to bring a laptop along, you'll need to research a particular electrical device and explain how it works in terms of the physics that we've been looking through. So that'll be the first SAC, and then the second one on the Thursdays is going to be a pretty standard test. So hopefully you'll be caught up on that stuff by that point. But if you're not, then you'll get this week's lessons to go over some of that stuff. But today's lessons on transformers. We've been doing a lot of stuff on power generation, on generators and the principles behind that. Now we're doing the other part of this topic, which is power transmission, how power is transmitted from one place to another, the physics behind that. And transformers is what we're going to start out looking at. This lesson's basically got 2 parts to it, so we'll go through transformers first, then look at power transmission in the second part. So a transformer, it's made of 2 sets of coils that are not in contact with each other. One coil is connected to a power supply, we call that the primary coil, while the other is connected to an external load, we call that the secondary coil. So we've got 2 coils, they're next to each other but they're not touching. The idea is that electricity flows through the primary coil, and then through some physics that we're going to look at, it's going to kind of almost transmit to the second coil. The idea is that as AC current flows through the primary coil is going to produce a magnetic field around it. So if you have a look at the diagram I've got there, you can see you've got your primary coil connected to the AC supply. The secondary coil isn't physically touching the primary coil. There's a little bit connecting them up, but we won't go over that for a bit. And the idea is that AC current is going to flow through the primary coil. The primary coil is going to produce a constantly varying magnetic field. So when we're talking about transformers, we have to have an AC current. If we have a DC current, it's not going to work. So that's just a kind of a little thing to keep in mind. Because the current produced by the primary coil is constantly changing, it produces a constantly changing magnetic field. Remember that if a wire is carrying a current in it, it produces a magnetic field. Because the current's constantly changing, the magnetic field's constantly changing, the magnetic flux is constantly changing, and because the secondary coil has a constantly changing magnetic flux through it, there's going to be an EMF induced in the secondary coil, which means current's going to flow through it. So the steps are: current through the primary is constantly changing, current through magnetic field through the primary is constantly changing, magnetic flux produced by the primary is constantly changing, magnetic flux through the secondary is constantly changing, and this is going to constantly induce a current in the secondary coil. So electricity flowing into the primary creates electricity in the secondary coil. That's the basic principle behind the transformer. Now, sometimes there'll be an iron core put between the 2 coils. The idea is that it kind of guides the magnetic field produced by the primary coil straight through the secondary coil. Rather than the magnetic field of the primary coil going off in all directions, it's almost all going to be directed into the secondary coil, which is going to help maximize the current induced in the secondary coil. So you get as much electricity in the secondary coil as you can, so it's working as efficiently as you can get it to work. So now we go into kind of the equations of how this is going to work. We've got a voltage in the primary coil, and we're going to have a voltage in the secondary coil. We've got the voltage in the primary V1, we've got the voltage in the secondary V2. Sometimes, and I think your textbook might do this, they use VP for V primary and VS for V secondary. I don't like to use that notation because in a previous lesson, V with a little subscript P on it was what we call the peak voltage, and if you've got the same symbols for the same different things, it can mix them up. So you'll see me using V1 and V2. Your textbook might use V primary and V secondary instead. They're the same things, but I prefer this notation just to keep things a bit clearer. So anyway, the equation that you've got there is V1 over V2 equals N1 over N2. The voltage in the primary divided by the voltage in the secondary is equal to the number of turns in the primary divided by the number of turns in the secondary. Remember that your primary and secondary coils have a number of turns in them. N1 and N2 tell you how many turns are in the primary, how many are in the secondary. So your example is you've got 10 turns of wire in the primary coil, 30 turns of wire in the secondary coil. What would the voltage in the secondary be if the voltage in the primary was 5 volts? So this is going to be a simple case of just plug your numbers into the equation that you've got. The voltage in the primary is 5, so V1 is 5. The number of turns in the primary is 10, so N1 is 10. Number of turns in the secondary is 30, so N2 is 30. You plug those in and get out one of those equations, and then you just rearrange to solve that equation. What you get out is that the voltage is 15 volts. So you've got 3 times as much voltage in the secondary as you have in the primary, because you have 3 times as many turns in the secondary as you have in the primary. So that's kind of what this next slide is about, that if the number of turns in the primary is less than the number of turns in the secondary, the voltage in the secondary is greater than in the primary. We call this a step-up transformer. It's stepped up the voltage to a higher value, and that's why it gets called this, just because it's got more turns in the secondary than in the primary. If you've got the reverse situation, more turns in the primary than in the secondary, the voltage is going to be less in the secondary. This is called a step-down transformer. The voltage gets stepped down. It's at a lower value now. So we've talked about voltage, how it gets either stepped up or stepped down depending on what your transformer setup happens to be. When you're talking about the power in the primary and the power in the secondary, we say that the power in those two has to be the same. So it's equal powers in the primary and the secondary. Remember that power is energy over time. So effectively, the amount of energy going to the primary in a given time has to be the same as the amount of amount of energy coming out of the secondary in a given time. Those two equal to each other. So I've said P1 equals P2, P being the symbol for power. Power is voltage times current. That's the second dot point there. P equals VI. So since the two powers are equal to each other, we can say the voltage in the primary times the current in the primary equals the voltage in the secondary times the current in the secondary. We rearrange, we get out an equation, V1 over V2 equals I2 over I1. So this relates the current and the voltage in the primary and the secondary coils all to each other. And if we then take our equation V1 over V2 equals N1 over N2 from a previous slide, and put that together with that equation, what we get out is the very last dot point here, what we call the transformer equation. It basically relates all the things you're going to be seeing in a transformer. It talks about the primary and secondary voltages, currents, and numbers of turns. It relates them all to each other. And the basic idea is that normally you get told 3 of those things and you need to use it to find a 4th one. And so you just pick whatever variables you've got in your question when you use your equation there. So it's just really plugging in numbers. As long as you've got that equation written down somewhere and you can remember how to use it, then normally you should be able to get most transformer questions correct. Now I've copied the transformer equation from the last slide onto this one as well. The reason I did that was to highlight a point, which is that if you look at the equation, the voltages and the number of turns have 1s up the top and 2s down the bottom. The current's got their reversed situation. So what that basically tells us is that if you've got a transformer that steps up the voltage and increases the voltage, it's going to decrease the current. If you've got a step down transformer which decreases the voltage, it's going to increase the current. So if voltage goes up, current goes down. If voltage goes down, current goes up. There's that relationship in between them, and that's going to kind of matter when we get into the next bit. So the next bit is what I call part 2 of this lesson. It's about actually the power transmission topic. So when electricity is transmitted through a wire, you're going to get some of that transmitted power lost due to the resistance of the wires that are carrying the current. The amount of power that gets lost is given by this equation. Power loss equals current squared times resistance. P loss equals I squared R. So the amount of power lost depends on the current. The power lost isn't going to depend on the voltage. It's the current that determines whether or not power gets lost in the wires. When you're distributing power, Power loss is something that should be minimized so that as much power reaches its destination as possible. You don't want heaps of electricity getting lost along the way due to the resistance of the wires. You want that to be minimized, and in order to do this, transformers are used to alter the current. So basically, we've got this picture, same as the one on the last slide. You can see that at the power plant, you've got a voltage of about 12 kilovolts. There's a step-up transformer, and that increases the voltage to about 400 kilovolts. I'm not sure if these numbers are realistic or not. I would assume so, but they illustrate the point that we need. So you've got your high voltage transmission lines transmitting the high voltage. That eventually reaches near a town or a house. There's a step-down transformer. Normally there's a couple, one at like a substation that steps it down a bit, and then one at a house out on like a power pole that steps it down even further. So you've basically got power plant, then a step-up transformer to make the voltage bigger. The power gets transmitted through the wires. Then when it gets to towns and such, step-down transformers are going to lower the voltage back to usable levels, about your household 240 volts. So the idea is that, maybe I talk about that. So the idea is that a step-up transformer is going to increase the voltage but decrease the current, and since the power loss depends on the current, if you've got less current, lower current, that's going to lead to less power being lost. So because you've got the step-up transformer increasing the voltage to a very high voltage, the current is going to go down. You want a very low current because that's going to minimize how much power gets lost in those wires. So that's just why they use the step-up transformer and have such high voltage transmission lines, because those lines are going to reduce the amount of power that gets lost along the way as the electricity gets from power plants to home. So I illustrate that with a bit of an example here. The example is electricity is transmitted through power lines which have a resistance of 16 ohms. Initially the current is 10 amps. What would the power loss be? So simple straightforward question. Power loss is I squared R, current is 10, so 10 squared, resistance is 16, so you times those together and get 1600 watts of power getting lost along the way. Then part B asks, if a step-up transformer was used to decrease the current to 5 amps, remember, step-up transformer increases the voltage, decreases the current, so the current's gone from 10 amps down to 5 amps. If the step-up transformer is used before the power gets transmitted, what would the power loss be now? So you've got the same equation, but now you've got a current value of 5 amps. Because of the squared factor, and because of the fact that you've halved the current, your power loss goes down to 400 watts, a quarter of what it was in part A. So you've got less power being lost. This is something that's desirable, and it kind of illustrates why people actually use transformers in this setup. So for the last slide, we're just looking at something that's related to power loss, and that's what we call the voltage drop. I calculated it in two different ways, one way in part A, one way in part B. Either way should get you the right answer. For some reason, I was getting the wrong answer for part B, and I'm still not entirely sure why. So it relates to the previous slides. So it says, using the numbers above, current of 10 amps and resistance of 16 ohms in the wires. If the voltage at the power station was 500 volts, how much voltage is going to reach the house? So your initial power is given by voltage times current, power equals VI. So your voltage was 500, your current was 10, so you started out with 500 times 10, 5,000 watts of power, power at the power station. Now, we know from the previous slide that when there were no transformers being used, the power loss was 1600 watts, so the power that actually got to the house was 5,000 watts, take away 1600 watts, 3400 watts actually getting to the house, and the voltage in the wires that gets to the house is going to be the power of 3400 divided by the current of 10, so 340 volts. So you start with 500 volts, you end up with 340 volts actually reaching the house. You can figure out that there must be what we call a voltage drop of 500 take away 340 equals 160 volts. 160 volts of electricity getting lost between the power station and the house. Now, that was for the case where there were no transformers being used. For part B, it says how much voltage would reach the house if the step-up transformer from before was used. I've done this in a different way. I've calculated the voltage drop as being the current in the transmission wires times their resistance. With the transformers, you've got a current of 5 amps because the current has been stepped down, times 16 ohms of resistance equals 80 volts of voltage in the wires being lost. So you can figure out that if you started out with 500 volts and you lost 80 volts along the way, this time you'd have 420 volts actually reaching the house. So you've got less voltage being lost, a lower voltage drop. I've done this calculation in a different way because sometimes use the first approach, sometimes use the second, but the point either way is that you get less voltage lost if you use transformers to step down the current when the power is being transmitted. So that's basically it for of today's stuff, last lesson of power generation and transmission. Just keep in mind that if you weren't in class last week, last week, then what you should be doing over the next coming lessons are going to Edrollo and watching the videos around that. I won't be recording videos since we've already kind of covered that stuff in class, I guess. But the idea is that if you were in class, then you should just be working on revision stuff. If you weren't in class, you should be catching up on the stuff you've missed. The PowerPoints for all that's up on Compass, so you can always access those if you want to catch up on whatever you missed. And you can always just send me through questions if you're unsure about anything. But that is basically it for today.